Okay, we're back and we got our mole map, so we're ready to go with that. And we'll call up our first problem. We'll see where we're going. And this one we want to know the mass of 0.873 moles of potassium thiocyanate. So if we go look at our mole map, we'll see at this point we're at moles, and we want to go over here to mass. So the mole map says to multiply by the molar mass. So each one of these things written between the arrows is the way to get there. You either divide by it. If you see the X in this case, it's on top. That means you're multiplying by it. The X is on the bottom. That means you're dividing by it. Here you're either multiplying by 22.4, dividing by 22.4. Here you're multiplying by 6 times 10 to the 23rd. You're dividing by 6 times 10 to the 23rd. Here you're multiplying by the molarity, dividing by the molarity. So we want to go from here to here. So what we need to know is the molar mass of potassium thiocyanate. So we're going to get that from, we'll go back up here, potassium thiocyanate. We need the formula. And in that case, the formula for potassium thiocyanate, oops, looks like we didn't go back to the proper page. There we go. Is KSCN. This is a positive one. That's a negative one. So we're going to take 0.873 moles, and we're going to multiply by the molar mass of KSCN, which in that case is going to be, we're going to add up the molar masses, 39.1, 32.1, 12.0, and 14.0. So that's going to be 2, 6, 15, 17, 6, 7, 8, 97.2. And if we cancel those, then we hopefully will get this answer that's buried under here of 84.68. So if we take 0.873 times the 97.2, you'll see we get that correct answer. Now, in the second one, this time we have liters of a gas. So our conversion this factor this time is going to be that one where we use our friend, the 22.4 liters per mole. So in that case, we're going to start at moles. We're going to go to gas volume, but we're at gas volume and we want to go to moles. Then we're going to divide by 22.4. So in that case, a little bit different than what we were doing before. We'll take 36.4 liters and we will divide by 22.4 liters per mole. And it looks like we get 1.58 moles of xenon. These are all one-step problems. This time wants to know molecules of water, and we start with moles. So if we know molecules and moles, here's number of particles is a molecule. We start at moles, we multiply by 6 times 10 to the 23rd. So we'll just simply take 5.22 moles, and we'll multiply by 6.02 times 10 to the 23rd molecules in a mole. And if we do that, we get 3.14 times 10 to the 24th molecules. Now, this time it wants to know how many potassium atoms are in 5.25 moles of this. This is a formula unit or a molecule. But it wants to know potassium atoms. So this is going to require an extra step. So we're going to take our 5.25 moles of potassium oxalate. We're going to multiply by 6 times 10 to the 23rd. And then what we're going to do is we're going to multiply by how many potassium atoms are in every molecule, which is 2. There's 2 K atoms in every molecule of K2C2O4. So our answer is double what we would have normally calculated. So when we do that, we'll take this times this times this. So that's going to be essentially that answer there, the 6.32 times 10 to the 24th. Now we're going to move into our multiple step problems here. And we'll get into those here in just a second. and get it. Go in there and get it. Go in there and get it. So that's what we're going to do at this point, is we're going to go in there and get that. And we will so what we're going to look at now is the you may have missed this problem up here. I'm not sure whether it shut off on me a minute ago, but in this one I took the 5.25 moles of the potassium oxalate multiplied by 6 times 10 to the 23rd molecules in a mole, because that's a molecule. But it asked me for atoms, so then I had to multiply by how many atoms were in each molecule, which there's 2 potassium atoms in every molecule. So I found the number of molecules by multiplying the moles by the molar mass, or not the molar mass, the Avogadro number, and then I multiplied that by 2 just to double that. Alright, so then what we're going to look at now is we're going to look at this problem. It's going to be a multi-step problem. This time what we're going to have to do is we're going to deal with multiple problems in one step. So this time I want to know the volume of a gas, but I'm starting with the mass of a gas. So in that case, we're going to look at we know the let's go back to the problem. We know the mass of the gas, and we want to get to volume. So if we go back to that mole map, we're at gas volume, and we'd like to get to mass. Or if we're at mass, we'd like to get to volume. We're either going to go this way or this way, depending upon what we're given. So it's going to involve a step to the middle and a step out, or a step to the middle or a step out, depending upon which one of those you're trying to do. So in this case, we're trying to take, we want to know the volume, so we're starting with mass. So we're going to take the way to get from mass to moles then would be, we take the 122 grams of SO2, we're going to divide by the molar mass of it, which is 1616, and this is 32.1, which is 64.1 grams per mole. Then we're going to multiply by 22.4 liters in a mole, because that'll cancel the moles. And then, so that's about 2. 2 times 22 is about 42. So this is a hair less than 2 times 22 is about 44 liters. So that's 42.7 liters. If these aren't exact, that's okay, because these look like these. But, I mean, I'm not doing the math at this point just to see what's going on. So how heavy would this many formula units, molecules of this be? So what we're going to do is we're going to take the 3.33 times 10 to the 25th formula units, and we're going to divide by 6.02 times 10 to the 23rd. Then we'll have to multiply by the molar mass of this thing, which that's going to be a big molar mass, because we're going to have to take 1 chromium, 6 manganese, and 24 oxygens. So that's 24 times 16. That's 1 times. So that's FUs in a mole. And then we will multiply by the molar mass of this. Chromium is 52.0. And manganese is 54.9. I'm going to go out. I've got a little program here that will calculate my molar masses for me. So I'm going to type in the molar mass. I'm going to type in the formula here. And it says that it's 765.6 grams per mole. So I know you know how to do that part. I'm just going to go ahead and save that step so we can get through this a little faster. And so I'll take this divided by this. This is 25th. So that's about a half. So that would be 500. So it's like 50 moles. and then take 50 times that, and you get a huge answer there, so 42,350. Sig fig wise, that's probably too much. I probably would have put 42,400, something like that. So that's a lot. That's a lot of molecules, a lot of atoms. Now I want to know how many oxygen atoms are in this many grams of ammonium carbonate. So now we're going to go from grams to moles to, we can't go to oxygen atoms because this is a compound. So this is going to be one of our longer problems. If you can do this kind, you can do any of them. So we're going to want to make sure we can see this. We've got 5.28 times 10 to the third grams of ammonium carbonate is NH42CO3. I'm going to use my little program again to get the molar mass. And that's 96.1 grams per mole. So we'll divide by the molar mass. And then we'll multiply by 6.02 times 10 to the 23rd. Now this is ionic, so that would technically be a formula unit per mole. So notice grams cancel, moles cancel. This is a formula. We want atoms, so in that formula there's 3 oxygen atoms. So I'm going to say 3 atoms of oxygen in every formula unit. So then the formula units will cancel. So we'll take that 5,280 divided by 96, 6.02 times 10 to the 23rd times 3, and it looks like we get 9.93 times 10 to the 25th. Let's just verify that that's correct. And that looks pretty good. 9.93. I got 9.92. We can live with that. And so there's your correct answer there. So how many moles are in this many molecules? That's an easy one-stepper again. We'll take 4.2 times 10 to the 22nd molecules. And then we'll take 1 mole over 6.02 times 10 to the 23rd molecules. And we just want to know moles, so this is going to be a one-step problem. And that looks like that's 0.07. All right, I'm going to break it off here at number 14, and we'll get a new video here for part 3 of this. Thank you for watching again, and tune into the next.